In this video, we're going to review chapters 5 and 6 for the final exam. So if you remember, chapters 5 and 6 were when we were talking about trigonometry, trigonometric functions, graphing trigonometric functions, and then I'm going to save chapter 7, which was our third trig chapter, for a separate video. So in our first problem, we want to find the amplitude, period, and horizontal shift of the following function. So we have y is equal to -5 times the sine of 4 times x plus pi over 4. So this is nice, the way that it's been given to you, because the 4 here is already factored out. So remember, if that 4 was not factored out of the inside of the function, you would need to do that step first. But here it is, so that saves us a little bit of time. Okay, so first we need to find the amplitude. And if you remember, the amplitude is the number next to the sine or cosine function. So this is going to come from this -5. However, amplitude is a height of a wave. And we don't measure things in negative units, so we always assume that our amplitude is positive. So in this case, our amplitude is just +5. Now for the period, what we want to do is start with the original period of sine, so that's 2 pi, and then we're going to divide by the number that's multiplied by the inside of the function. So in this case, that number is 4. So we're going to do 2 pi divided by 4, which gives us pi over 2. Okay, and then finally we want to find the horizontal shift, or sometimes you see this called phase shift. Okay, so that's another way you could see it named. The horizontal shift comes from the number that's added or subtracted on the inside of the function. So in this case, we have a positive pi over 4, but remember that horizontal transformations tend to do the opposite of what you think they do. So if you're adding pi over 4, you're actually going to go pi over 4 to the left. So it's like you're subtracting pi over 4 from all of your original points on the graph. Okay, so the next part of this question says to graph one complete period of the function. So let's look at our answer choices. Okay, so my strategy here would be to eliminate answer choices that clearly will not work. So the first one that I see that won't work is this one down here. Because the period here, so if we look from -pi to pi, so if we look at the length of this x-axis, this is a distance of 2 pi, but we said that our period was pi over 2. So this graph can't be the graph we're looking for. Now the other ones, even this one up here, is actually a period of pi over 2, so we need to keep that in mind for now. So let's see why we can eliminate some more. So let's see, they all have an amplitude of 5. So I guess this is going to come down to the phase shift. Okay, so maybe let's start with, let's pretend we were going to graph this by hand and start with what our key points would be for the sine graph. So our original key points, and remember these mean the points on the x-axis. So we have 5 of those. And originally, since our period has length pi over 2, we would go from 0 to pi over 2, and then we fill in those equidistant points in the middle. So between 0 and pi over 2, we would have pi over 4, and then we'd have pi over 8, and then we'd have 3 pi over 8. Okay, so if we're going to shift all of these points pi over 4 to the left, that means we're going to subtract pi over 4 from each of these. So let's see what our new key points end up being. So we have -pi over 4, positive pi over 4, and then we have 0 in the middle. So you could find the other two, but if we're trying to cut our time down, it might be enough just to find these 3. So now I can cut out this choice here because that graph doesn't go between -pi over 4 and pi over 4. So now I'm down to the choice in the upper left and the choice in the bottom right. And what distinguishes these is you'll notice one is basically the other one upside down. So if you take the one in the top left and flip it around 180 degrees, you get the one in the bottom right. So we need to decide which one this is. Well, if you go back and look at the original function, we have a -5 multiplied by sine. So that negative tells us that we want a reflection over the x-axis. So when we graph a sine curve, normally we would start at our first key point and we would go up to the top, back down to the middle, down to the bottom, and back up to the middle. But when we flip it, we want to start at our first key point, go down, go back up to the middle, go up, and go back down. So actually, our correct sine graph is this one down here. Because notice this one was the flipped one. Okay, so be very careful with that when you're dealing with shifted sine graphs, because you might have been inclined to choose the top left only because it looks like a flipped sine graph if it hadn't been shifted left and right. Okay, so that's graphing one complete period. So for our next problem, we want to find the period of y equals 3 times cosecant of x plus pi over 2. So to do that, we do the same sort of thing as we just did. So cosecant is actually 1 over sine, so it applies most of the same rules as sine. So the period here, we're going to take 2 pi, because that's the original period, and we're going to divide by the number that's next to x. But in this case, we don't have a number next to x, so we assume that it's 1. So our period just stays 2 pi. Okay, and now we want to graph the function. So when you graph cosecant and secant, a lot of times it's easier to start with the sine graph, and I know that that's difficult since we have computer-drawn pictures here, but let's see if that helps us. So our sine curve here would just be 3 times sine of x plus pi over 2. Okay? So maybe let's write down the original key points and our key points when we shift it horizontally, just like we did in the previous problem. So our original key points, since our period is 2 pi, we go from 0 to 2 pi. And then in the middle we have pi, pi over 2, and 3 pi over 2. Okay? In this function, we're adding pi over 2 to the inside, so that means we're actually going to subtract pi over 2 from each of our original key points. So we get negative pi over 2, 0, pi over 2, pi, and 3 pi over 2. Okay, so we know now where this sine curve should have key points. So let's sort of draw in the sine curve on each of these cosecant graphs. So let's see, look something like this. And then this one would look like this. So remember that basically the sine curve touches the cosecant curve at each of those little parabola type shapes, and it crosses the x-axis where the asymptotes are. So then this one would look like this, and this one would look like this. Okay, so now we need to decide which of these sine curves matches what we want. So maybe let's start by looking at whether it's shifted correctly. So we know that we want a period to go between negative pi over 2 and 3 pi over 2. So let's see if any of those don't fit that. Well, this one in the top left does not, because we see we have an asymptote at negative pi, and then we have an asymptote at 0 and an asymptote at pi. So this can't be correct because we know that the period has to start at negative pi over 2. So that one can't be it. Okay, this one down here, let's see, we have negative pi over 2 to 3 pi over 2, so that one's okay. And then this one in the bottom right, Again, we have a period between negative pi and pi, so we know that this one can't be it either. Okay, so now we're going between the top right and the bottom left. So the big difference between these is one is basically flipped and one is not. So when we're graphing a sine curve, let's think about what we would do in each of these situations. So in our function, we have a positive 3 in front of the sign. So at our first key point, so at pi over 2, we would want to go up first. In this one, we're going down and then back up and then up and then back down. So this would be like if we had a negative 3 outside of the sign. Whereas this one in the top left, notice we start at negative pi over 2, we go up, we go back down to the middle, we go down and back up. So this one is the graph that we're looking for. So my advice on those would just be to take your time, because a lot of times the graphs will look really similar. So just make sure that you're not making some careless mistake with how you're getting the points. Okay, in our next problem, we want to find the degree measure of the angle with the given radian measure. So if you remember, when you want to convert angles, we use this conversion factor. So we have pi radians per 180 degrees. And you might have to flip this fraction depending on whether you're converting into radians or converting into degrees. This time we're starting in radians and going into degrees. So we have 17 pi over 18. And then since we're going to degrees, we want to put 180 on top and pi on the bottom. So what this is going to do is make our pi's cancel, and then we're going to end up in degrees. So if you were to put this into your, well, we don't have to actually put it in the calculator. 18 goes into 180 10 times, so 17 times 10. Oh, sorry. Oh, no, this is right. Okay, 17 times 10 is just 170 degrees. So that is your degree measure. And you could have just plugged that into a calculator. Okay, for problem 4, a sector of a circle of radius 60 miles has an area of 1,400 miles squared. Find the central angle of the sector in radians. So a sector of a circle is like if we have a circle, and think of a sector sort of like a pizza slice. So it's basically like the slice that starts in the center and goes all the way out to the edge. So we're finding the area of this piece of pizza, basically. So the formula for this area of a sector is area is equal to pi r squared times some angle theta, where theta is in radians. Okay, so let's plug in what we know. So we know the area is 1,400. We have pi, we know the radius is 60, and we want to find the central angle theta. So all we need to do to solve for theta is just divide by pi times 60 squared. So we have theta is equal to 1,400 divided by pi times 60 squared. And if you put that into your calculator, you should get roughly 0.124 radians. All right. For number 5, we want to find the exact value of the trigonometric function. So we're given cosecant of negative 630 degrees. So exact value means we want to use the unit circle. So let's figure out what negative 630 degrees is on the unit circle. So the way I'm going to do this is I'm going to convert this into radians, because that's how I think better. But if you wanted to count degrees on the unit circle, that's fine too. So if I want to convert this, we have pi over 180 degrees. And if we put that into the calculator and simplify, we should get negative 7 pi over 2. So let's think about where that is on the unit circle. So we have 0, pi over 2, negative pi over 2. So if I start counting at 0, I go 0, negative pi over 2, negative 2 pi over 2, negative 3 pi over 2, negative 4, negative 5, negative 6, negative 7. So negative 7 pi over 2 falls up here. And so we know that it behaves the same way as positive pi over 2. So cosecant of negative 630 degrees is actually the same as cosecant of pi over 2, which is 1 divided by the sine of pi over 2, which is just 1 divided by 1, which is 1. So that is how we find the exact value. In this next problem, we want to find the values of the trigonometric functions of theta from the information given. So we're given that the cosecant of theta is 2, but our angle is in quadrant 1. So anytime you're given a problem like this, and we'll see this a little bit later as well, but make sure that you get a triangle first, so that way you can get any trig function you want from that triangle. So we know our angle's in quadrant 1, so we're going to draw our triangle in quadrant 1. So this is theta, and cosecant is 1 divided by sine, so we can say that the sine of theta is equal to 1/2. And if that helps you get the triangle a little easier, great. So because the sine is 1/2, we know that the hypotenuse is 2, and the y side is 1. So we can use Pythagorean theorem and get the square root of 2 squared minus 1 squared, which is the square root of 4 minus 1, which is the square root of 3. So the missing side of the triangle should be the square root of 3. And now that I've solved my triangle, I can find any trig function that I want. So we already found sine, but I'm just going to write it again so that we have it all in one place. So we have sine, cosine, tangent, cosecant, secant, and cotangent. Okay, so sine was 1/2, cosecant was 2. Now let's find cosine. So from the triangle, cosine should be root 3 over 2. So that means secant is 2 over root 3. And then finally, tangent should be 1 over root 3. So cotangent must be just root 3. And that is all there is to number 6. Okay, in the next problem, we want to find the exact value of each expression in radians. So once again, this means we're going to have to use our unit circle values. So for the first one, we have sine inverse of root 3 over 2. So we want to think of the angle. Okay, maybe I should remind you of this. So when we do inverse trig functions that are not dealing with equations, so we'll talk about it a little bit differently in chapter 7, but for the purposes of these types of problems, remember that sine inverse, our answers all have to come from that right side of the unit circle between negative pi over 2 and pi over 2. Okay, so we need an angle between negative pi over 2 and pi over 2 that has a sine of root 3 over 2. So because the sine is positive, we know that it should occur in quadrant 1. So we need a quadrant 1 angle that has a sine of root 3 over 2. So this would be the angle pi over 3. For part B, we want to look at cosine inverse. So remember, answers for cosine inverse need to come from the top of the unit circle, from 0 to pi. So we want the angle between 0 and pi that has a cosine of positive 1/2. A cosine that's positive tells us it has to be in quadrant 1. So the quadrant 1 angle with a cosine of 1/2 is again pi over 3. Okay, and then our last example for this is tangent inverse of negative square root of 3. So for tangent inverse, it behaves a bit like sine. We want answers from the right side between negative pi over 2 and pi over 2. Okay, so we need an angle with a negative tangent, so it must be in quadrant 4. So we need the angle in quadrant 4 with a tangent of negative root 3. Well, if the tangent is negative root 3, we know that the sine must be root 3 over 2. So this angle must be something with a denominator of 3. And you might think that we want to say 5 pi over 3. So that's normally what we would say, but in the case of evaluating these functions, we want to make sure that we stay between negative pi over 2 and pi over 2. So a way to rename 5 pi over 3 so that it falls into that range is negative pi over 3. So for this one, this is actually the answer that we would want, not the 5 pi over 3. All right, for problem 8, we have an 86-foot tree casts a shadow that is 110 feet long, and we want to find the angle of elevation of the sun. And we want to round our answer to 1 decimal place. So this question might seem a little confusing at first just because we're told about a tree and then it's asking about a sun. But let's think about what this situation looks like. So we've got an 86-foot tree, so let's assume that that's like, some tree right here, and this is 86 feet tall. And it casts a shadow, so we might have this horizontal line coming from the base of the tree that's 110 feet long. And we want to find the angle of elevation of the sun. So if the tree is casting a shadow, the sun must be somewhere up here. And there must be sort of this imaginary line from the tip of the shadow up to the height of the tree and up to the sun. So our angle of elevation is the angle between the bottom and this imaginary dotted line, so we're going to call that theta. So now you notice we have a situation with a right triangle, and we've got some angle and 2 sides. So we should be able to relate this using some trig function. So in relation to theta, 86 feet is the opposite side, and 110 feet is the adjacent side. So we can relate these two with tangent. So we can say tangent of theta is equal to 86 over 110. So to solve for theta, I can just take the tangent inverse of both sides. So I get theta is tangent inverse of 86 over 110. And if I were to plug that into the calculator, you should get roughly 38.0 degrees. So that's rounded to 1 decimal place. In this next problem, the first thing we want to do is sketch the triangle, and then we're going to solve it using the law of sines. So first, we're given that angle B is 27 degrees, angle C is 53 degrees, and side B is 48. So remember that when you label a triangle, we label the side opposite the angle with the same letter. So for example, in this first one, if angle B is down here, side B would be this side over here, side A would be this one, and side C would be this one. So it might help us to go through and label all of these really quickly. So let's see, on this one, this would be B, this would be A, and this would be C. This would be B, A, and C, and this would be A, B, and C. So we're looking for the triangle with angle B equal to 27. So right away, I can knock out a few of these. So this one, angle B is not 27. So we can knock out that one. Now we want angle C to be 53. So in this one, angle C is not 53, so we can knock that one out. And then finally, I want side B to be 48. So the only one of these two triangles where side B is 48 is this one over here. So that is our triangle. Okay, now I want to solve this triangle using the law of sines. And we want to round all of our answers to the nearest integer. So we still need to find angle A, side A, and side C. So those are the 3 things that we need to find to complete all of our angles and all of our sides. So maybe first, since we already have 2 angles, let's find angle A. So angle A is going to be 180 because all the angles in a triangle add up to 180 degrees, and we can subtract off angle B and angle C. And if we do the subtraction, we should get that angle A is 100 degrees. So that's angle A. Now maybe let's find side C. So for side C, we're going to set up a law of sines equation. So remember, for this, you need 2 pairs of sides and angles. So in this case, I have the angle B side B pair. So I'm going to say sine of 27 degrees over 48 is equal to the sine of 53, which is angle C, over side C. So notice the only variable I have now is side C, and so we can solve for that. And so if I solve this equation for C, I should get 48 sine of 53 degrees over the sine of 27 degrees, which if you put that into the calculator, you should get around 84. So make sure for these that your calculator is in degree mode, because notice that all of our angles are in degrees. Okay, and the last thing we need to find is side A. So once again, we're going to set up a law of sines equation, but instead of side C, we're going to use the angle A side A pair. So we have sine of 27 over 48 equals sine of 100 over A, which tells us that A must be 48 times sine of 100 over sine of 27, which if you put that into the calculator, you should get about 104. So that is solving a triangle using law of sines. Okay, in this next one, we want to solve triangle ABC, and we want to round all answers to one decimal place. So this one is one of the difficult triangle problems because notice we have two sides and an angle. And that angle has the same name as one of our sides. So when that happens, that's that type of problem where we could have three different cases. So this problem could either make 0 triangles, 1 triangle, or 2 triangles. So before you even solve the problem, the first thing we need to do is see how many triangles are actually made by these two sides and the angle. So the way we do this is we check the height of the triangle. So in this case, we're going to have h is equal to c sine of b, which is 168 sine of 41 degrees, which comes out to be about 110.2. So the important thing to notice about this height is that it's less than side b, so it's less than 129, and it's also less than 168. So maybe I should restate that. So 110 is less than 129, and 129 is less than 168. So when you get this chain of inequalities like this, it tells you that we're going to get two triangles. Okay, so let's draw our picture for two triangles. So we've got this situation going on. So always label the given angle as this corner over here. So this will be angle B. And then your other angle on the other corner over here should be C, because that was the other side we're given. So this angle is going to be C1. This angle is going to be C2. And then this is where it gets a little confusing. This big angle at the top is going to be A1, and this smaller angle here is going to be A2. And then let's label our sides. So we have side B, side C. This big bottom side is going to be A1, and this smaller bottom side is going to be A2. So just as a reminder, the two triangles that we're looking at are the big outside triangle and then this skinny triangle in here. Okay, a lot of people get that confused with the isosceles triangle, but we're actually looking at the red triangle and then the big blue triangle. Okay, so let's figure out everything we need to find. So let me see here. We need, let's draw our little box so we make sure we don't forget anything. So we're going to have angle B. Or actually, you know what? We already have that. So I'll just put the things we need in the box. So we need angle C1, we need angle C2, we need angle A1, and we need angle A2. And as for the sides, we need side A1 and side A2. So those are the 6 things we need to find. So I would start with the angles. They tend to be a little easier. So the first thing you always want to find is that angle opposite B, so we want to find C1. And so to do that, we can set up a law of sines because we know side C. So we can say sine of 41 over 129 is equal to the sine of C1 over 168. And if we solve this for C1, this says that C1 is equal to sine inverse of 168 sine of 41 over 129. So if we put this in the calculator, C1 turns out to be about 58.7 degrees. So make sure again here that your calculator is in degree mode, because if it's not, your answers will be all off. Okay, so we found C1. So now all the other angles actually come a lot easier. So for the big blue triangle, we already know angle B and we know angle C1. So to get angle A1, we can just do 180 minus B, which is 41, minus C1, which is 58.7. And doing that subtraction in the calculator, we should get A1 is 80.3. Okay, so angle A1 is 80.3 degrees. Okay, now maybe let's find angle C2. So angle C2, we notice that if this triangle here is isosceles, then both of these sides must be length B. So that means both of these angles must be C1. So the way we can get C2 is take 180 and subtract off C1. And that gives us 121.3 degrees. So C2 is 121.3 degrees. And the last angle we need to find is A2. So now that we know B and C2, we can find A2 by simply doing 180 minus 41 minus 121.3. And that should give us 17.7 degrees. So A2 is 17.7 degrees. So we found all of our angles. The last things we need to do are just find side A1 and side A2. And to do this, we're going to have to go back to the law of sines, and we're going to use the angles A1 and A2 that we just found. So for A1, we can do the sine of 41 over 129 is equal to the sine of 80.3 over side A1. And if we solve this for A1, we'll get A1 is equal to 129 sine of 80.3 over sine of 41, which if you put that in the calculator, you should get 193.8. So A1 is 193.8. And the last thing we need to do is just find side A2. So the sine of 41 over 129 is equal to the sine of 17.7 over A2. And this tells us that A2 is going to be 129 sine of 17.7 over the sine of 41. And so A2, if you put that in the calculator, should be about 59.8. All right, so that was the big long two triangle problem. And our last problem in this video is going to be to find the area of the triangle whose sides have the given lengths. So if you remember, we had two formulas for the area of a triangle. So one was 1/2 AB sine of theta, and one was called Heron's formula. And this one dealt with side lengths. Okay, so depending on what you're given in your area problem determines whether you're going to use the first formula or the second formula. Okay, in this one we were given 3 side lengths, so I'm going to use Heron's formula. That's not to say that you couldn't use the other one, but this one would be a lot easier. So to do Heron's formula, we need two things. First, we need the semiperimeter, which is 1/2 all the sides added together. And then our area formula is going to be the square root of this semiperimeter times the semiperimeter minus each of the sides, like this. Okay, so the first step for Heron's formula, though, is find the semiperimeter. So for that, we'll have 1/2 times 11 plus 115 plus 116. And if we put that in the calculator, we should get 121. So then I can use 121 for S in my area formula. So I'll have 121 times 121 minus 11 times 121 minus 115 times 121 minus 116. So you could type this all in one step, but I'm going to go one step further just to avoid some careless errors. So this will be 121 times 110 times 6 times 5. And so if you were to plug this step into the calculator, it should give you an area of 631.9 units squared. So we weren't really given a unit in this one, so I'm just going to leave it as units squared. And this is the area of our triangle. So keep studying. Chapters 5 and 6 covers a lot of material, and in the next video, we'll do some more trig with chapter 7.